I know, and I'm glad. I don't know. It's just, I don't care. Am I recording this? Yeah, I'm actually recording this. Look at that. First equation, how do we solve that? Subtract 4. So 2/5 x equals -4. Now what? Divide by 2/5 or multiply by 5/2, right? That's the same. Dividing by 2/5 the same as multiplying by 1/2, so that cancels. X equals 2 goes into 4 twice, so -10. Does that make sense? What? Is that okay? Good. How do you do the next one? Combine like terms, so it's 11x plus 7x, that's 18x, minus 24x, -6x equals 24. So divide both sides by -6. -4. Good. Yeah? You did that one wrong?
Yeah, for some reason I got
I wasn't threatening anybody. No, you got a much smaller number than 4. Oh, yeah. Okay. Yeah. What do we do here? Distribute. 3x minus 3 equals 2x plus 4, right? Now what? Add 3. So x equals 7. Yay. That's it. Okay. Now, we're still, again, we were going to move away from solving equations very soon. I mean, we'll still stay with us, but it's kind of important. That's why I'm still, giving you the same kind of looking stuff every day. But um, I want to talk a little bit about real numbers. Did we talk about real numbers? Not real. If you go back maybe to even like day 1, did we talk about real numbers? Properties of real numbers, good. Did we talk about um, like different sets of real numbers? Adding properties. Yeah, we haven't, which is good. Doesn't seem like we have. So let's talk about real numbers. So, can somebody, by the way, how many of you heard the term real numbers? Say, yeah. How many of you heard about numbers that are not necessarily real? What? It's okay. We don't have to. Well, you're not going to talk about numbers that are not real for a while. But yeah, that's right. Good. That's okay because I just taught that in college algebra, so it's you got some time to get comfortable. But give me examples of real numbers. One, good. I like that one is real. Give me another example. -1, very much real. Give me another one. What? 9, sure. Give me something more fun. Over 17? Yeah, that is that a real number? Sure. How about pi? Is that a real number? Yeah. How about square root of 2? Is that a real number? Sure. So every number that you can kind of experience, walk into the store and tell them, give me square root of 2 pounds of fish, they should be able to do that. It'll be actually very hard. But if you go to the store and tell them, give me square root of 2 feet of lumber, they technically should be able to cut, exactly square root of 2 feet of lumber. Okay? Now, do you know where the real numbers live? Yeah, where do they live? If you want to send 5 a letter, do you know where that letter is going to go? Where 5 lives? What? Yeah, it lives right on the number line, on the real number line. Right? And I'm not joking. This is real stuff. We have real numbers, and what makes a number real is that we can touch and smell it and find it on the real number line. Okay? But there are different sets of real numbers. And the first set that we talk about is the set of natural numbers. Okay? So the natural numbers are what we use to count. We say these are the counting numbers. Or positive whole numbers. Okay? So that's 1, 2, 3, 4, 5, and so forth. These are natural numbers. Now, when we talk about the sets, or in mathematical sense, we use these curly brackets to represent that we're talking about a set. And then we'll list the elements in that set. So for the natural numbers, it's 1, 2, 3, 4, and blah, blah, blah. Okay? Those are counting numbers. The first numbers used by our civilization. And there's a special symbol that represents the set of natural numbers. It's kind of it's a capital A with a little twist, something like that. So big double-legged N. So that's the set of natural numbers. Okay? Just positive whole numbers, 1, 2, 3, 4, 5. So as we agreed, these numbers live on the number line. So if I draw a number line, I got 1, 2, 3, 4, and so forth. Okay? Are there any gaps or holes on my number line right now after I just placed 1, 2, 3, 4? Do you think there are going to be numbers between 1 and 2? Yeah. There are going to be numbers to the left of 1? Yeah. So I want to fill this entire line, by the way. I want to find all the numbers so there are no gaps or anything like that. All right? I want to have a nice continuous street of numbers. But so far we only got 1, 2, 3, 4. And there's a bunch of stuff between 1.2 and 1.3 as well, right? There are infinitely many numbers between 1.2 and 1.3, right? Yeah. Well, okay, here's 1.2 and 1.3. Well, I can put 1.22, right? 1.222 and 2222222. I can keep doing the 2. It'll still going to be in between those two. And then I can just do whatever. I can go 1, 2, and then make stuff up. It'll still be less than 1.3. So I can just keep piling. Yeah, I can pile them all up in there, right? How well? Because I can. I'll work very hard at it. But instead of listing them, at least I'll group them into separate sets and be able to fill them out. But you have to realize that between any two real numbers, there's going to be another one. No matter how close you think they are, you can always find one in between by just taking the average of them. Oh, they're pretty close. But again, between 1 and 2, they're, infinite. There's more than elements in the universe between 1 and 2. That's many numbers, because you can always do that. Yeah. It says the special term for that phenomenon is called the real numbers are dense. No matter how close you think they are, there's always going to be one in between. And no matter how you get even closer, because we can play this game and I will win every time. If you give me, a number, I can always get it closer to the next one and whatever. But so far, natural numbers. The next set that I would like to introduce would be the set of integers. So this is just whole numbers. Positive, negative, 0 is an integer. So I will list it in this fashion. So all the negative numbers, all whole negative, whole positive, 0, those are integers. And we have a special symbol for the set of integers. It's a capital Z with a little twist in the middle like that. Now, please notice how every natural number is also an integer. Right? Every natural number belongs to the set of integers. Yeah, so you're just throwing in negatives and 0. So now if I go back to my number line, so that gives me 0, -1, -2, -3, and so forth. Okay? I still have gaps. Do you agree with that? Now, what goes in between those numbers? What goes in between 1 and 2? What can you do? What kind of numbers go in between 1 and 2? Yeah, decimals, right? The fractions. Do you agree with that? So if you think about the human civilization, we first learned how to count, and then we learned how to do fractions. The negative numbers came in much later. Because negative numbers kind of weird. They're made up, right? Remember how you mentioned something about imaginary numbers? Mia, right? Are you with me? Yeah. Well, if you think about this, we're totally comfortable with negative numbers. We're not being freaked out by -1. Hey. But if you think about it, that's kind of made up. If you think about -1, what does that mean? Weird. But anyways, but the fractions came in basically together with counting, because if I can count my cows, and I want to trade you a cow for a goat, that's kind of a crappy deal, right? I want to do half a cow maybe. That's a fraction. That's how the fractions came about. So those are rational numbers, we call them. Rational numbers. So these are your fractions, the numbers that can be expressed as the ratio of two integers. So if you can do integer in the numerator, integer in the denominator, you got yourself a rational number. So numbers that can be expressed as a ratio of two integers. Okay? So one way to see that, if you have a number that has a decimal, you just look at the decimal expansion of a number. If that decimal part has a pattern, a repeated pattern, it will make it a rational number, because there will be a way to write it as a fraction divided by a fraction. But few examples of rational numbers. Can you give me a few examples of numbers that can be written as a ratio of two integers? Integer in the numerator, integer in the denominator. 3/4, I like that. 3/4 is clearly a rational number. Give me another one. All right, -2/3 is clearly a rational number. It's a ratio of two integers. -2 and +3, or +2 and -3. How about 7? Is 7 a rational number? Sure. I can write 7 as a ratio of two integers. 7/1, 21/3. I got options. Because I can always express 7 as ratio of two integers. So every integer is also a rational number, because I can take every integer and put it over 1. Yep. Every natural number is also an integer and is also a rational number. So rational number is kind of a bigger set that includes all the integers. Let's not generalize here. But things like 0.111111, that's a bad example. How about 0. Is that okay? No, 0.0111. All right, I don't like that one. How about just let's do threes. That's easier. 3, 3, 3 goes on forever. So there is a pattern, right? There is a repeated pattern. It's always 3, 3, 3, 3, 3, 3, 3. That can be expressed as a ratio of two integers. In this case, it's 1/3. So every time you see some kind of a repeated pattern where part of a number keeps reappearing, if I do this, it's 1, 2, 3, 1, 2, 3, 1, 2, 3 forever, that is a rational number. I can actually, yeah, I can find two integers, which, I'm not sure what they are. No. It's going to be some, it's weird. I'm not that good to just see that. Hey, what can I say? You lucked out. But when you see a repeated pattern, that is a rational number. All right. So we go back to our real number line. So we got all those little fractions in between each number. So the question is, are we done? Is that continuously filling that line, or there are still little gaps? Oh, this is taking forever. You understand what I'm trying to do here? Okay, I'll stop. So all the little fractions. Now the question is, are we done? Is that going to fill the line, or there are still going to be numbers that are not rational, numbers that cannot be expressed as a ratio of two integers? And that is a big question. Can there be a real number, the one that I can smell and touch, but I cannot write it as a ratio of an integer divided by an integer? And the answer is yes. Yes. There are numbers, and we call them, oh, by the way, we use a capital Q with a kind of a twist to represent the set of all rationals. Now, there is a set of irrational numbers. So these are the ones that cannot be expressed as the ratio of two integers. That means when you look at it, the decimal goes on forever and ever and ever, never stops, and doesn't have any patterns. There's no repetition in it. Pi would be one of those. Okay? Pi is a number that we cannot write as a ratio of two integers. Square root of 2. Right? If I do square root of 2, it's not a proof that it's a rational number, but if I actually plug this in my calculator, okay, that's statistics. If I do square root of 2, where is it? I'll just get a big pile of digits that will go forever, ever and ever and ever, and doesn't have a pattern. And we can actually prove that square root of 2 is never going to equal to the ratio of two integers, no matter how hard you try. I'm not going to do the proof, but it's there. So it's one of those numbers. So square root of 2, square root of 3, square root of 5, square root of 7. Square root of 7 plus 1 over 5, it's one of those numbers. So you can always do that. 2 pi is one of those numbers. Pi over 3 is one of those numbers. So we can always do that. So there are a lot of those, okay? But it gives us a little philosophical issue. Is it still a real number? Can I actually walk to the number line and pinpoint the location of square root of 2? So this is precisely square root of 2. But I don't know what it equals to, because it's never, the decimal will go on forever without patterns. So that's, right? Can you measure? You know what I'm trying to say? Can you find square root of 2 on the number line? But so far, rational numbers cannot be as ratio of two integers. So the decimal goes on forever with no patterns, basically with no repetition. So not like 1, 2, 3, 1, 2, 3, 1, 2, 3. So some examples would be numbers like pi, square root of 2, 3 pi. There are many of those numbers. Square root of 3 plus square root of 2, and so forth. There are infinitely many of those numbers as well. But, and are they still real? I'm just going to tell you, yes, they are. And I can show you something. I can show you how to construct square root of 2. That's the easiest one to build. To actually draw a line that's precisely square root of 2 feet or inches long. Okay? So pretend you're going to, I don't know, Home Depot, and you want to buy a square root of 2 feet of lumber. And they will not be able to just go, with the ruler and cut square root of 2 feet of lumber, because you don't know where it is. Right? You kind of know it's for fun, of course. You just walk in and you just puzzle people, because that's what it is. I mean, can you find it on a tape measure or whatever? No, right? Because of all that expansion thing. But if I walk to Home Depot and ask them, can you give me 2 sticks that are exactly 1 foot long? Can you do that? Precisely 1 foot. And then give me another stick that, let's say, 5 feet long. Just a longer stick. They can do that, right? Okay. So I have those 3 sticks. Let me see. Here's one. Here's another. And a much longer one. All right? So I'm going to do this. I'm going to take 1 stick. I don't know why I'm doing it in this fashion, but can I place them so they form a 90-degree angle like that? Is that possible? Without doing any harder movements? Can I just place 2 sticks in a way that they form a 90-degree angle? Yeah. It's not, well, it's close enough. It's close enough. Come on, guys, you're missing the point. All right, so 1, 1. And I'm going to take that other stick and I'm going to put one end of it at that corner, and, so it kind of touches that. Can I do that? And then I'm going to make a cut right here. I'm just going to cut that. So the question is, how long is this stick right here? How do you know that? You're just guessing? That's a very educated guess, because that's what I'm trying to build. Yeah, because if I ask you, name 1 theorem of all of mathematics, you should all name 1. Pythagorean theorem, right? You all know Pythagorean theorem? Yeah. What does that say? If you have a right triangle, one side is A, one side is B, and the hypotenuse is C, what is the relationship? A squared plus B squared equals C squared, right? So if I call this side C, then I have 1 squared plus 1 squared equals C squared, right? And what is 1 squared? And what is 1 plus 1? 2. So I get 2 equals C squared. So what is C? Yeah, C equals square root of 2. So I just, what? No. You see, I have a square of a number equals 2. Then that number has to be square root of 2 by definition. So that means I just built something that's precisely square root of 2 feet long. Right? Therefore, it's real. Here we go. I'm touching square root of 2. I can take this stick. I can place one end of that stick at the origin, and the other end will fall somewhere here, which will be square root of 2. Okay? So now all those numbers, rationals together with the rationals, they will fill in that entire number line. What? That has nothing to do with what I'm talking about. Now, we do not have a fancy symbol for irrational numbers. See, like everything had a fancy symbol. Irrational numbers do not. And also, remember how before we were saying that every natural number is an integer, every integer is a rational number. Well, irrational numbers are just complete opposite. They're completely separated. There's nothing in common. There is no number that is both rational and irrational at the same time. They're completely separated. But the set of all real numbers is all of that. It's rationals together with irrationals, and we have a special symbol for that, which is capital R with a little twist. Yeah, all real. So all rationals together with all irrationals. So that's a capital R with a little twist. There is a story behind all of that. We mentioned the Pythagorean theorem. Do you all know that guy, Pythagoras? You know when he lived? What? Long time ago. How long? Was it 1800s or 1800s on the other side of the... Yeah, so those things, right? The Greeks, the ancient Greece. So that's... Sure. But, and again, the reason why this theorem is called Pythagorean theorem, not because he came up with it. That theorem was known way before him, the pyramids and all that. They used all that theorem. He probably the first one who said, hey, that's the theorem. He maybe proved it for the first time. There are many proofs of that theorem. There's a Garfield's proof of that theorem after the U.S. President Garfield. Do you know about U.S. President Garfield? He was, I think, the first president who got shot. Yeah. Yeah, he was the first president who got assassinated. But there is a mathematical proof of that theorem called, I think, yeah, he's the first president who got assassinated. I think it was before him. Let's see. I'm not, I'm just, let's see, President, again, don't quote me on that. There is a Garfield's proof, quote me on that, President Garfield. Yeah, died 1881, so that's after Lincoln, right? Yeah. What? Am I even talking about the same president? Did he get shot? Yeah, assassination. He got shot. So yeah, that was after Lincoln. Then I'll take that back. But there is a Garfield's proof. I hope so. Now I'm doubt everything. Garfield's proof. Yeah, it's a Pythagorean theorem. Garfield's proof of the Pythagorean theorem, yeah. So anyways, maybe he wasn't the first one who got shot. Sorry about that. But anyways, there's a Garfield's proof. But the Pythagoras, he had a society that called themselves Pythagoreans. And they believed in the perfect structure of the world and the universe. And everything is pretty and... Oh, yeah. Oh, believe me. And if you think about that society, the ancient Greek society, what else do you know about that? Olympics, right? Everyone's kind of, ugly babies thrown off the cliff type of group of people, right? So everything is pure and beautiful. So the structure of the world, the rational numbers, that's as bad as it gets. Every number can be written as a fraction, and that was their strong belief that there are no irrational numbers. And they held that belief very strongly. But then they were the ones who did this. Hey, look at that, square root of 2. I just built the square root of 2, therefore it must be real, while it's not rational, so hey, what gives? And they tried to keep that a secret, because otherwise the whole thing will crumble. Their structure of the perfect world, all of a sudden. And there was a guy among those members of the society who, did one of those, put a note on the door, like the, later with the church. Yeah, but it was way, way before that. Said, hey, watch out, there's square roots of 2 out there. So they killed that guy as a punishment for spreading. They tried to keep it a secret, and it's kind of fun if you read about that. And that society still exists. It's still an active one of those secret societies. They call themselves Pythagoreans. Yeah, it is active. Yeah. Well, now I'm not sure because now I have to doubt my historical references. But last time I checked, well, I haven't sent them the membership fees or anything like that, but they still hold that belief that there are no irrational numbers, that irrational numbers cannot be real. So everything is fraction. As that's the worst as it gets. I have no idea. Don't ask, because I don't know. There's secret society. It probably has like 4 members. I mean, there are still societies that hold on the whole, turtle and 3 elephants and the Earth stands on that. Have you seen those ancient pictures? Yeah, you know what I'm talking about. Like, this is the world. Stands on like 3 elephants. The elephants hold the planet. Yeah, and the Earth is flat. There's still, flat Earth society. Yeah, they probably do. I'm not joking. It has, they have like, 80 members, but there's still like a flat Earth society. If you Google that, it'll probably show up. Flat Earth society. Yeah. So, anywho, that was all good and fun. So now you know about real numbers.